In this session, let's look at the process of graduation and the various statistical tests that are used for testing out the graduated rates. So, what do we mean by graduation first of all? In the context of insurance premium settings and aspects relating to mortality rates, when we define the word graduation, it is more of a process of smoothening, a process of smoothening the mortality rates data, right? I collect the mortality rates data from the real world observations. Think of it like this, right? Let's say I am investigating a set of people, a big, huge sample of people at different age groups, x plus 1, x plus 2, and so on. So I'm looking at a large sample of people in each of the age categories and how many of them have died within each of the category. So from there I'm trying to get an estimate of the mortality rate out of the number of people that are observed in each of the rate category, in each of the age category. I'm trying to find out what is the proportion of people that have died during the observed period, generally a 1 year kind of a period. And based on that, whatever is the mortality rate out of X people whom I have observed, probably 2% of them have died with an age equal to X. Out of N people that are observed, 2% of them died within the next 1 year during the observation of 1 year period. 2% of them have died whose age was equal to X. Now, like that, for each age category, a separate estimate of the mortality rate is obtained. So that particular estimate of the mortality rate obtained from the real world observations of the data or real world investigation, we are calling as crude mortality rate. But with respect to this crude mortality, there could be some kind of a problem where the values may not be smooth over the ages. Probably it may so happen that during the observation period, people with age 20 might have died more compared to people with age 21. And again, with age 22, again the numbers would have been lesser or the proportion would have been lesser. Now, how do I justify that people at 21 die lesser compared to 20 as well as 22? In general, our understanding is with the age, the mortality rate can keep increasing, at least for most of the ages. With as the age is increasing, we see that the mortality rate can keep increasing. But when I use the crude mortality as it is, it might very well be possible that the mortality rates are not smooth, which means the premiums which I am trying to design based on the mortality rate, it may so happen that I may charge a higher premium for a 20-year person or probably lower premium for a 20-year person, a higher for a 21-year-old person, and again lower for a 22-year. If that's the case, a 21-year-old person will never come forward and apply for an insurance policy because it's no way working out. He'll think that probably let me wait for 1 more year, my premiums will come down. So it cannot create a kind of a satisfactory explanation, especially if the rates are not smooth. So graduation, whatever we are doing, The key intention for it is take the initial crude mortality rates and apply some kind of statistical or mathematical practices or techniques on the top of those rates, so that two objectives. One, ensure that the rates are more and more smoother, and at the same time adhere closely to the actuals, adhere closely to the crude data. Not too much of deviations from the crude, but come very much closer to that crude observations that have been made. So the major intention is obviously to smoothen the mortality rates and try to reduce the error because of the sample that has been collected. Try to reduce that sampling error to whatever extent possible. Reduce the sampling error to a large extent possible, and probably see that as the ages are increasing, probably the mortality also keeps increasing and vice versa. But always remember, when I try to produce extremely smooth is a pattern with the age. When I try to produce extremely smooth kind of a data, adherence to the reality may be a difficulty. Adherence to reality may be a difficulty, and the more I am adhering to reality, the smoothness is a difficulty. So that's where we say it's a trade-off. A trade-off between smoothness. It's a trade-off between smoothness and adherence to the actual data. So probably I may have to define some level of adjustment to the smoothness, some level of adjustment to adherence, so that overall looks like a better graduation process, which is balancing between the smoothness and adherence to the actual data. Because in general, as I said, the main intention behind this process is, in general, we have a notion saying as age increases, right? As age increases, we see that the mortality rate, number of people dying during a particular period for that age group should be higher compared to a lower age group, but at least per greater number of ages, at least per maximum set of ages, this is the kind of a behavior that is going to get created. And at the same time, especially when I am designing the premiums for insurance policies which are based on these mortality rates, probably I would not be able to justify why for a 20-year-old person the premium should be lower, for a 21-year higher, and again for a 22-year-old person the premium is lower. Why should that happen is something that cannot be justified in the real world. So it's always better to smoothen the rates, right? Unless there is some kind of association that can really be thought of, it cannot be justified. So that is one of the prime reasons we get into the smoothening of the crude rates, so as to explain these aspects quite comfortably, and so as to make the pricing of the products quite effectively. Now I can look out for the distributions for number of deaths. Now I would like to look out for distribution for number of deaths, right? From the, if at all I have to apply all these things, if I am looking at the distribution, the smoothening process wise, I can see I can create a distribution for the number of deaths. So one way is I can assume that the number of deaths follow a Poisson distribution. I'm trying to create a distribution now to smoothen out. Apart from the crude rates that I'm following, based on the crude rates, I'm trying to find out a distribution for the number of deaths. So if I am assuming a Poisson model, so I can very well see that the distribution for the number of deaths at age X is following a Poisson distribution, wherein the lambda is what I am taking as whatever is the total exposed to risk. The total exposed to risk for this age X, I am multiplying it with the mu x plus half. Means the typical what you call the force of mortality. I'm taking a force of mortality at age x plus 2, x plus half. I'm taking the force of mortality at age x plus half, and that particular force of mortality I am multiplying it with the total central exposed to risk at that particular age X. That is what is giving me the distribution of deaths for a Poisson distribution, if I am assuming that the deaths are following a Poisson distribution. Now, if that expected value, I mean, if that exposed to risk is very large, I can very well assume this to follow approximately a normal distribution. Poisson distribution approximates to a normal distribution with the mean lambda and variance as lambda. So the mean is also the central exposed to risk multiplied by mu x plus half. Variance is also central exposed to risk multiplied by mu x plus half. So if I'm going with the central limit theorem assumption, the Poisson distribution will approximate to normal distribution under this kind of a scenario. So in general, if I am assuming that the deaths are following a Poisson distribution, I can model the death for a age X as a Poisson distribution with lambda as central exposed to risk multiplied by the force of mortality at age X plus half. But if I am assuming that the deaths are following a binomial distribution instead of Poisson distribution, if I am assuming that the deaths are following a binomial model, then what happens? The same logic. The deaths are following a binomial distribution with the exposed to risk Ex as the number, and I will not take the force of mortality. I am taking up the probability of death within the next 1 year. I am taking the discrete probability of death within the next 1 year. So here this is what is the model for the death, and again here also if the Ex is very large, the binomial distribution will get approximated to a normal distribution. Again, the mean of the binomial distribution will be will be exposed to risk multiplied by Qx with the variance as exposed to risk multiplied by Qx multiplied by 1 minus Qx, because the variance of the mean of a binomial distribution is NP and the variance of a binomial distribution is NPQ or NP into 1 minus P. So the variance of the approximated normal distribution also is NP into 1 minus P. So depending on whether the deaths are following a binomial distribution or a Poisson distribution, and depending on whether the exposed to risk is a very large number or a small number, I will use that distribution or an approximation to the normal distribution to identify the smoothened numbers with respect to the death rates, right? Why do we need to do all these things? Whether it is finding out a distribution, or smoothing out. See, what typically happens is at different points in time, I may want to use a comparison analysis. So, comparison between various products. What has been the death experience with various products, or probably the death experience over time. Is there more number of deaths versus less number of deaths across different points in time? Or probably I would like to compare my actuals with some standard tables that are already present, right? So, what could be the standard tables? See, generally we see two forms of standard tables, wherein we are looking at the tables that are prepared based on the national data, which are called as national life tables. They take the census data as well as the death registrations across the country, whether the person has insurance or doesn't have any insurance. This data is purely taken from the population of males, females, census related data and the death registrations that have occurred during a particular period, and based on that the mortality rates are determined. That is one set of tables, and second set of tables are the data based on the insurance companies. So whatever has been provided by the insurance companies with respect to the mortality experience. So based on the number of policies, number of deaths that have occurred during the period, they create one kind of table based on the actual experiences they had during a specific period. But these are the two major sets, probably something like ELT 15 males or ELT 15 females kind of tables come from the national data, whereas a table like AM92 come from the insurance companies kind of a data. But the prime reason at any point in time, looking at the actual experiences and probably comparing them with doing a graduation on them, then comparing across the various products or various time periods actually helps us to understand if there has been any kind of a difference from the other product, or is there any way some specific kind of people are taking some specific kind of policies corresponding to the others, or if there is any difference in the actual calculations, actual values compared to the table related values. All these things, all these comparisons are helping the insurance companies to make the necessary modifications to their pricing experiences. So that is where some of the consistencies which we would like to check out in this process is, okay, whatever are my observed rates, are they consistent with respect to standard table? Whatever is the standard table I am taking, I could have taken AM92 or ELT 15, whatever it is, whether if I have to test out whether my observed mortality rates at each of the ages are consistent with respect to the standard tables. With respect to the standard table, depending on whether I am going on a discrete note, I will be using QX. Otherwise, I am taking mu x plus half. So, from my standard table, I am considering these kind of values and I am taking the observed. So, typically, I am doing a statistical test saying with a null hypothesis saying the true mortality, the real mortality rates for each age, rates at each age are equal to the rates that are determined by the standard tables. So whether the rate is Qx or mu x plus half, there is a consistency between them. Sometimes we would like to do, especially whether to test out the fitness of the actuals to the graduated. Instead of directly looking at the standard table, I may look at it with respect to, so here for the standard table I'll put actually the S as a S as an indicator, QXS. So again, if I'm going with comparing it with the actual rates with the graduated rates at each age, they are more consistent with the graduated rates. The graduated rates are typically denoted as QX with just a circle on the top of it, mu x plus half with just a circle on the top of it. This is a comparison with respect to the graduated rate. Now, as I have already highlighted, we are primarily doing the graduation. So, I can compare the observed rate, the actual rate, I can compare it with a standard table, or I can compare it with my own graduated rate. And probably my own graduated rates, I can compare them with the standard table to see whether my experience is consistent with that of the standardized table. So whenever we are doing any graduation, we all know that it's a trade-off between the smoothness and adherence to the reality. But at the same time, we are also talking about the suitability for a purpose. Right, because the main suitability is determining the insurance premiums where I require smooth rates so that the premiums can be kept gradually increasing with the age. Otherwise, people at some age levels may not even take the insurance policies. So apart from maintaining a trade-off between the smoothness and adhering to the reality, I would also be looking at the suitability for a particular purpose. So when I am trying now the actual thing comes, when I am trying to compare the actual mortalities with respect to the graduation, comparing the actual mortality with respect to graduation, especially when I am using or with respect to graduation, if I am using, let's say, a Poisson model for graduating or smoothing, right? When I can use the graduated distribution as the Poisson distribution. So I would like to compare under the assumption that the deaths follow a Poisson distribution with a Poisson distribution with the central exposed to risk multiplied by the graduated mu x plus half, or probably I'll take the deaths will approximately follow a normal distribution with central exposed to risk mu x plus half, which is graduated, and the variance also being the central exposed to risk mu x plus half, which is graduated. So if at all I am using a Poisson model where I am trying to express the force of mortality at age x plus half. But if I am going with a binomial model, again the same, the dx, I am assuming that it will follow a binomial distribution with the initial exposed to risk qx, which is the graduated qx. Or with when ex is very large, I am assuming that it will follow a normal distribution with mean as ex qx and variance as ex qx into 1 minus qx, a graduated rate. So using the central limit theorem, and the only thing right now is the graduated rates, whether it is qx or mu x plus half, I am considering these graduated rates and then using the Poisson distribution model and then trying to compare it with my actuals. So here now comes the various tests. So first test is test for smoothness. Test for smoothness in the data. So whatever the graduation Poisson model or whatever the model we are using for the graduation purpose, the best way to test for the smoothness is take the third difference. Whatever the model which we are using, take the third difference of the graduated rates. When I say third difference, yes. Okay, for let's say 30, 31, 32, 33, so on up to 40. I got some graduated rates A, B, C, D, so on up to let's say K. I got a set of graduated rates K. Let me call them as mu x plus half. This is what I got based on a graduation model which I have used. Let's assume it's a Poisson model that I have used. Based on the Poisson model that I have used, I got the graduated rates like this, right? So if I am saying third difference, okay, the first difference delta, in this case, when I am trying to compute the first difference delta, this is A minus B, this is B minus C, this is the first difference, this is C minus D. So these are the first differences. Then similarly, I am trying to get the second, the third. That is the way I am trying to find out the differences. So probably the other way, I mean probably let's write the delta. It is B minus A, C minus B, D minus C, and so on. Similarly, I am taking delta square, C minus B minus of B minus A, D minus C minus of C minus B. So actually the delta square is coming out as C minus B plus A. So it's coming out as C plus A minus 2B. This is coming out as D plus B minus 2C. That is the second difference. And when I am talking about a third difference, I am getting it as D plus B minus 2C minus of C plus A minus 2B. So it's actually coming out as D plus 3B minus 3C minus A. So this is what we call as the third difference. So for every 4 rates, if I find out this D plus 3B minus 3C minus A, this is what I call as the third difference. Right? In case of this third difference, if the third difference values are very small with respect to the original graduated values, the third difference values are very small with respect to the original graduated values, then we say that this particular graduated rates are very smooth. And at the same time, the third difference is they progress regularly with age. As age is increasing, you see that the third difference is slightly increasing also. So the important test with respect to testing for the graduation is the third differences should be much small when I compare them with the original graduated rates, and along with they being small, they should increase gradually with respect to age. When these two things are happening, we can very well say that this particular graduated rates are more and more smoother, right? So that is one important test we can use for the testing of the smoothness of the graduated rates. Alright. Now we have to look out for the testing of adherence. This is one major test for testing the smoothness in the data. But the next thing which we are going to look out for is the testing for adherence. Test for adherence to the actual data. Adherence to the actual data is another mechanism wherein the various tests are available. So the first of those which I am going to look out for is the standardized deviations test. I am looking out for the standardized deviations test. So depending on whether I am using my graduated rates, whether I have used a Poisson distribution to estimate the graduated rates or a binomial distribution to estimate the graduated rates qx naught, I would be using a standardized deviations test. So for the standardized deviations test, what I am looking at is for each age, I am looking out for the actual number of deaths or observed number of deaths at this particular age minus the expected number of deaths. The expected number of deaths using the Poisson distribution model or using the normal approximation of the Poisson distribution is I take the central exposed to risk and multiply it with mu x plus half graduated and divided by the standard deviation. We know that the variance is the central exposed to risk mu x plus half, because if it is following a Poisson distribution, the mean and the variance are the same, which is the central exposed to risk multiplied by the force of mortality at age x plus half. So as a part of the Z computation, we say x minus mu by sigma. So it is going as the expected, the actual observed number of deaths minus the expected number of deaths divided by the standard deviation of the number of deaths. So this is under the assumption that it follows, the deaths are following a Poisson distribution and I have graduated the rate using the Poisson distribution model. So this is what we are using for testing whether the graduated rates are adhering to the actual data or not. Similarly, when I am going with estimation of QX, which is based on the binomial distribution model, the ZX again which I am using is being comparison of the deaths at each age with respect to the mean, normal distribution approximation of the mean of the binomial distribution, normal approximation of the binomial. So the mean is the exposure to risk multiplied by graduated QX, and the variance is exposure to risk multiplied by QX multiplied by 1 minus QX. Right, this is the variance, so I'll put a standard square root under it to give me the standard deviation. So I will look at it with respect to a normal distribution. I'll compare compare this with respect to a normal distribution to compute the Z. So I'll compute the Z at each of these aspects by computing the standardized deviation, and based on this Z that gets created for each of the ages, I get the Z for each of the ages to see whether my data, whether my observed data is fits the graduated rates. I am using a chi-square test to test whether my actual data is fitting the graduated data. I am using a chi-square test where I am defining the chi-squared as the summation of all this zx squared across all x's. I am trying to see the chi-square is the summation of this zx squared. So whatever is this, I'm comparing whatever this value that I'm getting, I'm comparing it with a chi-square distribution. And okay, how many degrees of freedom I have to use, because every comparison with a chi-square distribution, I have to find out the degrees of freedom, right? Generally depends on the kind of graduation model that is being used, right? We'll discuss about it slightly later, but depending on the degrees of freedom that is being used, we will try to look out for depending on the model that is used for the graduation purpose, we'll try to use the degrees of freedom accordingly. So our calculated values are compared with the chi-squared values. So if the calculated values are much above the critical chi-squared value that we get from the table, then we can say we can reject the null hypothesis. What the null hypothesis was the actual data is coinciding more or less with the graduated rates. So if I am rejecting the null hypothesis, means there is a large deviation between the actual rates and actual observed rates and the graduated rate. So I cannot go ahead with the null hypothesis. Or otherwise, if at all we are seeing that the sigma zx squared is much lesser than the calculated value, then probably I can very well go ahead saying there is no strong evidence at 95% or 99% level of confidence that the graduated rates are much deviating from the observed rates. So the chi-square test, whatever we are using here, it's a one-tailed test, because I'm more bothered about only on the higher side, right? Typically, if I'm looking at the chi-square test, so as long as my zx squared is not greater than this particular value, I'm not rejecting the null hypothesis. Only if my zx squared is greater than the value. If it is lesser on the other side, I'm not bothered much. So if the larger the values of the test are there, then only I am concluding that the observed number of deaths are quite different from the expected number of deaths, which I calculated using the graduated rate mechanism. So that is where only if only if the observed zx squares are very much higher than my critical value, then I would be rejecting the null hypothesis, and based on that I would be concluding that the observed number of deaths or the actual death experience is much different from the expected numbers which are computed using a graduated mechanism. But in this model where I am using the chi-square and finding out the individual zx and then squaring and then adding and checking out whether this total is greater than one critical value, the biggest drawback which I could see is there could be very few small deviations, but one large deviation. Now, when I square it and add up, probably because the squares of these numbers are very small, though this is very large, the overall summation could still be lesser than a critical value. So, because this overall summation may be less than the critical value, we may say that the graduated rates are more or less, the actual rates or observed rates are more or less coinciding with the graduated rate. Though we see in one or two ages, the graduated rates are very much deviating from the observed, but because of we taking the overall scenario and looking at the comparison of the overall value rather than individual values, the large deviations might be overlooked because of many small deviations that could be present. And okay, the other way that could come out is, okay, the z values for all of them may be negative, very small but negative, right? Once I take a zx squared, it may not be that high above the critical, but all individual zx's, let's say I am seeing them as negative, but squares will be positive. So all of them may be negative or all of them may be positive, which means it's an indication that my graduated model, whatever I am using, if the observed minus the expected, they are all positives, then it means the graduated model is undergraduated, because all of them, the actual deaths are more than what are being estimated. So, but overall, through this chi-square test, the test is still getting passed. I mean, I'm not rejecting the null hypothesis, because overall the sigma zx squared may not be greater than the critical value. But individually, when I am looking at their zx's, all of them are positive or all of them are negative. That also is one major drawback that could not be covered by this chi-square test. And the other thing that could come out is, there could be a lot of biasing. Okay, up to certain age groups there is a negative, whereas after that there are certain age groups there is a positive. Some kind of grouping could be there in the individual data, in the individual zx's, apart from the overall zx squared. See, only if the overall zx squared is greater than the critical value, I am saying that the actual data may not be, the observed data may not be adhering to the graduated rates. But if zx squared is less than the critical value, directly I am saying that there is no evidence that I can reject that statement. So I may be forced to go ahead with that statement itself. But what we are seeing is three major drawbacks can occur because of that. One, as I have already highlighted, some large values, some large deviations may be overlooked because many other deviations are very, very small, or probably the entire data may be overgraduated or undergraduated, but overall sigma zx squared may not be greater than the critical value, or there could be some groups of ages wherein up to a certain group there is a negative undergraduation, and after that there is a overgraduation, but again sigma zx squared is not so significant that overall the model is coming out as not a fitment to the graduated rate. So that's where using a standardized deviations and squaring the standardized deviations and comparing with the chi-square test, though it is one of the better models to be used, it has these kind of limitations which are addressed by a few other tests which I am going to look out for them now. So out of them, one such kind of a test which I am trying to look out for is the standardized deviations test directly, without doing a squaring of them and all. I am doing a standardized deviations test itself, wherein my intention is to see if the small number of large deviations, this was one of the problems as we have highlighted, small number of large deviations are offsetting the large number of small deviations. If small number of large deviations are getting offset by large number of small deviations, so that the overall sigma zx squared is still lesser than a critical value based on the chi-square test. And finally going ahead making a conclusion that there is no significant difference between the observed rates and the graduated rate. So that is the main intention of using the standardized deviations test. So what we do is, whatever the zx's we are computing, the zx's are nothing but they are values from a standard normal distribution. They are nothing but the values from a standard normal distribution itself. So what I can very well do with them is, I can split the whole see the typical normal distribution values. Okay, -3, -2 standard deviations, -1 standard deviation, 0, 1 standard deviation, 2, 3, and so on. So what we are saying is, okay, split this entire interval -infinity to -3, -3 to -2, -2 to -1, something like this, -1 to 0, 0 to 1, 1 to 2, 2 to 3, and 3 to infinite. Let's say I have split this entire interval like this, and look at the actual z's that we have computed here by comparing the actual with the graduated. Try to find out how many z's are there in each category, and you also know how many z's should be there if at all they are coming from a normal distribution. If at all they are coming from a standard normal distribution, how many z's should be there? So out of let's say 100, we say that -1 to +1 standard deviation, -1 to +1 standard deviation, 68% of the values should lie. So by symmetry, probably -1 to 0, I require 34% of the observations. 0 to 1, I require 34% of the observations. Similarly, we say -2 to +2 standard deviations, 95% of the observations should lie. 95% means 47.5 this side and 47.5 to the other side. So going with that, 13.5% observation should lie here, 13.5% observation should lie here. Like that, I can assess if the data is coming from a standardized normal distribution. I would see how many how many should come into each of the categories. So overall we can check out if there are very huge, okay, if there are many values coming up here, because as per the normal distribution here we should not find actually any kind of values, right? So either here or here you find a large number of values, or probably between this we are not finding a good set of values. You can directly reject the null hypothesis and say that no, this is not coming from the standardized normal distribution, which means the null hypothesis wherein the graduated rates are more adhering to, or the actual rates are more adhering to the graduated rates. That kind of an assumption can very well be rejected. Of course, we'll be taking the numericals corresponding to each of these aspects and tests, but just to understand the conceptual perspective behind all these things and behind the conceptual intention behind these tests, we are trying to look at all these things. And typically, so see what we typically see otherwise also is, on a broader scale, if I am having a 50% of the observations, 50% of the observed zx's, if they are lying between -2/3 to +2/3, a direct one single quick test to work out, if 50% of them are lying within the interval of -2/3 to 2/3, or 50% of them are outside this interval. If 50% of them, 50% or more are outside this interval, we can reject the null hypothesis and say that the graduated rates are not a representation of the actual rates. right? So we can very well go ahead and we can take up whatever the number of ages. Let's say I have taken 20 ages. I am simply seeing 10 of them. If they are not lying between minus 2 by 3 to plus 2 by 3, then we can very well reject the null hypothesis. So the same logic we can use whether we are using a binomial distribution or a Poisson distribution for estimating the graduated rates, right? So that's why, so either I can do for each of the groups, right? Either I can do for each of the groups separately, identifying how many are between minus 3 to minus 2, minus 2 to minus 1 and so on, or as a quick test I can see if 50% of my observations are outside the minus 2 by 3 to plus 2 by 3 kind of limit. See, generally in case of outliers, as a quick check, we can also see like any individual standard deviation, if at all any single zx is less than minus 2 or greater than plus 2, right? There should be some kind of a concern that the fitment is not that proper, or probably very much less than minus 3, very much greater than plus 3. They are going to cause some kind of concerns that the fitment of the graduated rates with the actual rates is not that proper. So that is how we can use, first we can try out with the chi-square test using the standardized deviation, and secondly, because the problem of chi-square test is, the problem of the chi-square test is some large deviations can be very much offset by large number of small deviations. So to observe that particular aspect, we are giving importance to each and every observation at each and every age group, trying to find out individual ZXs, assuming that they come from a normal distribution, trying to see how many of them are falling in each of the categories, and if they are not falling as per the normal distribution mechanism, we are rejecting the null hypothesis and we are going ahead with the alternate hypothesis, making a conclusion that the actual rates are not adhering to the graduated rates, right? Now, one more important drawback which we have seen with the chi-square mechanism is the overall rates can be either overgraduated or undergraduated, right? Probably when I am looking at the ZXs, it may be possible that all ZXs may be positive or all ZXs may be negative. But each one of them may be very small positive, very small negative. So that when I am trying out the ZX squared, it may be small, all of them may be small and positive, and the summation may not be so high that it exceeds the critical value. So that way the chi-square test is not able to find out or not able to test whether the overall graduated rates are overgraduated or undergraduated. So so we are trying to address that particular mechanism using the science test. Science test, while standardized deviations test was trying to address one of the drawbacks of the chi-square test, wherein some large deviations can be offsetted by a large number of small deviations. The science test is trying to test out whether the overall graduated rates are undergraduated or overgraduated. So for this, we are trying to test out based on identify the number of positive signs that are there in the Z. Number of positive ZXs. See that think of them to be some n. The number of positive signs that are there, that they assume that there are n positive zx's. If in the actual data, let's say I got n number of positive zx's, but the number of age groups that I had, let's say is some m. Now the science test, what it is doing is, you assume that n follows a binomial distribution with m and 1 by 2. So you are looking at n as a binomial distribution with m and 1 by 2, right? And of course we can find out, okay, the mean. What is the mean of this binomial distribution then? M by 2, and variance is m into 1 by 2 into 1 by 2. M by 4 is the variance. So we can very well find out the mean and the variance for this. So what you can see is, if the actual observed number of positives is much lesser than probably the mean, let's say if I am making a normal distribution assumption, mean minus 1.96 times standard deviation, or if my n is greater than mean plus 1.96 standard deviation, we will reject the null hypothesis and say there is either overgraduation or undergraduation. But if my n's are lying within this range itself, then I cannot comment on the overgraduation or the undergraduation. So that's where this test becomes a two-tailed test, because I am checking out for the deviation both on the lower side as well as on the higher side. More number of positive zx's, we are seeing that actuals is greater than the expected. Means the expected rates are much lower. So you can say that there is a lot of undergraduation that is present on the graduated rates. Similarly, when you are seeing that the number of positives are much lesser than the mean minus 1.96 standard deviation, then we can say that more number of negatives are there, which means the expected rates are much higher than the actuals, means there is a lot of overgraduation that is present. So what could very well be done is, one, I can use a normal distribution assumption of the binomial and then go with the mean minus of 1.96 standard deviations, or we can go with mean plus 1.96 standard deviations, and we can test out whether it is greater than the other. Otherwise, I can purely restrict myself to the binomial distribution itself. Right? I can very well go with the binomial distribution itself, wherein if I am really wanting to find out based on the positives that are there, right, you can very well check out, okay, this is the binomial. So we know that for the binomial distribution, the probability density function is ncx p power x 1 minus p to the power n minus x. So this is the probability for each one. So if I want to find out the probability above a particular value, right, if I want to find out the probability above a particular value, then all I am trying to find out here, the probability with respect to p, here I will still take my p to be 1 by 2 itself, and the number of values I am taking it as m. So probably the same expression will become mcx into p is 1 by 2 to the power x. This 1 minus p also becomes 1 by 2 to the power m minus x. So actually the same general probability density function will work out to mcx into 1 by 2 to the power m. So what we are trying to say is, now from, let's say, x equal to 0, for p of x equal to 0, this becomes mc0 half power m. P of x equal to 1, this becomes mc1 into half power m. So like that, I want it in such a way that the probability of this side less than this particular number as well as greater than this particular number, this should be probably 0.5, 0.05 or 5%. Probably this could be 2.5. This plus this put together should be overall equal to 5%. So probably I know the m. Based on this, I will decide what is that particular n. Based on this, I have to find out what is that particular value of x here, wherein the summation of all these things, will be lesser than the 2.5%. The highest value of n or highest value of x, where the summation of all these things is lesser than 2.5%. So that is one way we can directly go ahead and then test out what is the probabilities that are associated with the values lesser than that. So probably if I am having 20, quick look at, if I am having 20 observations and there are only two positive signs. So what I could take is, I'll take with respect to 0, I'll take with respect to 1, and I'll take with respect to 2. So if the 2 is falling toward this side or here or here. Now what I could do, 20, if I am talking about 0, I am saying 20c0 into 1 by 2 to the power 20. Similarly, if I am talking about 1, 20c1 into 1 by 2 to the power 20. Otherwise 20c2, 20 into 19 by 2, 190 into 1 by 2 to the power 20. Now these are the three numbers that are there with me. So what I would try to do is, okay, the first one, what is the probability? The second one, what is the probability? The third one, what is the probability? If the summation of these three is still less than 2.5%, then I can very well say that I can reject the null hypothesis. So that is one way you can quickly test out without using any kind of normal distribution approximation also, whether your actual rate, whether the graduated rates are getting adhered to the actual rates or not. We can find out the p-value for this. From that, probably I can compare it with 2.5%, and based on that comparison with the 2.5, I multiply it by 2, I get the p-value, and if the p-value is lesser than 5%, I can reject the null hypothesis and say there is an overall bias, either positive or a negative bias in the overall graduated rates. So either I can use a normal approximation where the mean is m by 2 and the variance is m by 4. I can compare it with m by 2 minus 1.96 times m by 4 as well as m by 2 plus 1.96 times m by 4. If my actual number of positive signs do not lie within this interval, then probably I am rejecting the null and saying there is a biasing. Whereas if it lies within that interval, I cannot reject the null hypothesis, so I cannot say there is any kind of overgraduation or undergraduation in the values. So we can even use some kind of continuity corrections also if required. So greater than less than minus 1.96 times or greater than plus 1.96 can really result in my actual values being whether there is over graduation or undergraduation. So if at all I want to test out for the same, as we are saying, a continuity correction, probably if I'm looking out on an undergraduation kind, or probably if I have 20 actual positive signs, or if I'm having 20 positive signs, it's better to go with 20.5, because I'm trying to check out whether the value, whether the numbers is less than. So wherever I want to check out for less than something, I will take 20.5. I'll take the higher side of it. Whereas my intention is to check for greater than something, I'll take the lower side of it as a part of my continuity correction. So here I can take a continuity correction of 20 to 20.5 and then do it with respect to the normal distribution assumption, and based on that try working out if my actual number of ZXs are less than mean minus 1.96 standard deviation or greater than the mean plus 1.96 standard deviation, I will go ahead rejecting the null hypothesis, right?